It's really a pleasure to be here today. I haven't been in this venue before, and it feels very conversational, and I hope that's the way it'll proceed. We're going to go through a number of different domains. We're certainly going to talk about precise copies of cities and what the implications are. But the path we're going to take has some turns in it, which is why I have this little quote up here. Well, it's a sort of semi-quote. Paul Hindemith was a German composer, conductor, who wrote a lot about composing music, and much of it has to do with where the audience is relative to where the composer wants them to be. And he talked about giving them enough sense of comfort where they are, that they're moving forward, and then taking turns that they're not expecting, and then allowing the audience to regather with him and to continue, and then another turn that's unexpected. This being a way of introducing surprise, which if we go to Claude Shannon, might be the definition of information, where something has changed. But today we'll take some turns, and at the end we'll have a chance to talk. So forgive me if these are hairpin turns at certain moments. Seeking a better understanding of how things work, we've talked about Egypt and music and so on. Much of this is all tied together just with pattern recognition. I'm keenly interested in trying to find patterns in the financial markets using genetic algorithms to forecast commodities and so on. Pattern recognition is the binding theme. So we'll consider a constellation of ideas today. I can talk a little bit about how some of it came about. I'm just going to run a couple of these. When I was young, I was very fortunate. I was raised in a musical family. My father was a composer, conductor, and a well-educated man, and so he gave me a lot of musical background. And when I was in my early 20s in 1977, I produced a record that became a million-selling record. And just at that time, I was keenly interested in Egypt, so I was able to actually hire Stanford Research Institute in partnership with others to excavate the Great Sphinx. So you'll see some images of the Sphinx in here. It was a fantastic opportunity to watch SRI at work, and how they gathered data and how they computed it and so on. And those were early days for field computing. So that will play into this as we go. So I've titled it Representations of Reality, because even though a city, a digital city, is a representation of a real city, there are many issues that surround this, having to do with how humans perceive and think and build mental models. And we're going to test some of our senses here today. So this box, this green box, is going to contain a series of words. It's an extremely long sentence. I'm going to go through it, phase it in, because it's one of my favorites that I've come across in technical literature. It was a collaborative paper talking about three-dimensional computing. So we'll just start, and I'll read it the first time, and then maybe in subsequent times you'll know where we're going. So smooth interactive animation is particularly important because it can shift a user's task from cognitive activity to perceptual activity, freeing cognitive processing capacity for application tasks. So because I work in a technology where we're modeling cities digitally, this was an extremely important piece of information for me. But it's a long sentence and it's packed with information. We'll come back to it again. I just wanted to start with a look at reality. There's a lot going on, and people generally have the sense that they're experiencing reality directly. So we're going to take a quick look. This will be familiar to you, those of you who have technical backgrounds, at the electromagnetic spectrum, which is gamma rays to radio waves. It's an extraordinarily wide expanse. But what we can sense is the visible spectrum. So we can see colors and we can see shapes, but these are all in a very, very small band. And the rest of this, the bounded yellow boxes here, are only detectable with instrumentation. So we can learn about these extensions of the electromagnetic spectrum, but we need equipment to do so. So the same is true with what we can hear. So now we've looked at eyes, now we're looking at ears. We have this acoustic band in sound, but then there's also infrasound. and ultrasound. In the course of preparing for this, I was looking at whales, the spectrograms of whales and bats and so on, and it's really remarkable how high the communication bandwidth is for these creatures. But we're excluded from all of that conversation, or most of it. So again, only detectable with instrumentation. So here I'm using an old friend as the example of an average human. And simply to say that good experimentation has shown that we take in about 10 million bits per second through our senses. The number's been established over and over again as a reliable range. So the new riddle of the Sphinx, for those of you who know the old one, the new one is how fast can we learn new information? So we've just seen that we're taking in 10 million bits per second. 20 bits is what we can learn. 20 bits per second. So it's it's 1/500,000th of what's coming in is what we can learn. These numbers were striking to me when I first saw them. So I checked them, of course, and checking across multiple disciplines. If we go to information theory, I've just mentioned Claude Shannon. The average information in human language is 1 bit per character, so think of letters. And learning by reading or listening, there's the number again, 20 bits per second. So now I go to neurophysiology. And here the number's a little higher. Conscious sensory perception is about 40 bits per second. But still acknowledging it's many orders of magnitude below the data that comes in by our receptors. So ergonomics, this is one of my favorite books actually, called Fitting the Task to the Human. We'll skip the big numbers and come back down to what's conscious awareness. They're estimating 16 bits per second. These are very, very low numbers. And lasting impressions are less than a bit per second. So I'm emphasizing bits per second here because jumping from millions to units is a big jump. So here I'm going to use an example just to sort of set up the conversation. Taking a hieroglyph, showing its constituent components, the way the word would sound, iteru, and its final meaning in English is river. So translating data into more intelligible forms is a powerful attribute of digital cities. So we might think of them as just a copy, a replica, but there's something much more profound that we'll see today as we go through this. So we rely heavily on our vision, and it's worthwhile asking a question. Does it tell us the truth? Now, I don't know if that looks like a steady image. Does that look steady? Or is it moving? Yeah. So it's actually completely static. It's a familiar effect. We've seen it before, but it's a remarkable collection of pixels that are not moving at all. And yet your optics, your retina, your optic pathway, your visual cortex are conspiring here. It reveals the machinery that's at work trying to make sense of certain types of inputs. So in some sense, it's revealing there's an illusory property that is part of our visual process. So we use this as a way to open a world. Here's a quote. Everything you experience by sight is your construction. And that's a pretty bold quote, but Donald Hoffman is a specialist in this area. And he's interested in the ideas that images reveal some of our hidden machinery. So I'll talk about Donald Hoffman, and I'm going to add to him Alfred Korzybski. These are two gentlemen who so Donald Hoffman is currently working. He's actually got a TED Talk you can look at. Korzybski was decades before, but a very interesting scientist. And the principal notion that they advance is that evolution only needed a nervous system that was good enough to get genes from one generation to the next. So it didn't have to tell the truth about what the world was. It just had to evolve in a way that was sufficient for DNA to move forward in time. So that was Korzybski's idea, and it's being broadly proven by Donald Hoffman, who's a professor at UC Irvine. And they would both appreciate this. This is a standard example of another illusion where, and confirm it if you will, the two dots are in fact exactly the same color. But there is no way that you can override this. Your visual system will tell you that they're different, simply because of context. So you may be familiar with these examples, but to me, the persistence of them, I've seen this hundreds of times, and every time I look at it, it's still just as amazing because you can actually get a colorimeter and measure these things, and they are identical, and yet I can't make them look identical when I'm looking at them. So the representation of information affects how we can understand and interact with it. And that's important in what's coming here, what we're going to talk about, representation of the information. And what that does is, if we know this, we can begin to understand how to tune the information so that it understands how to couple with the human perceptual and cognitive processes in a better way. So again, from that green box, I'm going to pull two words out: cognitive, which is thinking, understanding, learning, and remembering. And here I'm exemplifying that by a picture of the D-Wave quantum processor, a thing of beauty, as well as a profound computational device. And then on the other side, perceptual. So we're talking about freeing up cognitive bandwidth by letting our perceptual systems work. Perceptual makes inferences about the properties of the physical environment. And here I'm using a vaulted, or what they call a barrel ceiling hallway as a sort of comparator. This is not digital at all. It's a very analog, very deep and profound experience for us, and it's a perceptual one. We don't need to analyze it, although we could if we wanted to get into the filigree. So I'm making this assertion. Our experience of the world is analog. And we'll come to this later on in the talk and look at the idea of analog and digital and why digital is so important. And yet, ultimately, if we want to understand things, it has to go from analog into digital, take advantage of that whole world, and then bring it back to us in an analog form so that we can comprehend things in a different way. So here's that green box again. And I'm just going to run through this now that we've looked at cognitive and perceptual. Shifting a user's task from cognitive activity to perceptual activity. And here's the line that is really important: freeing cognitive processing capacity for application tasks. So when we get into the cities, I'll talk a little bit more about what that means to me in any case. So constructions of cultures, things that we've built. And here's one of these unexpected alternate paths. This is a project that I was a co-founder of and have been involved with for 40 years. We work at the pyramids. We started by excavating the Great Sphinx in '78, and then have radiocarbon dated the Great Pyramid. This is a lost city. Essentially, we did one test square to sort of look at a little space out here in the sand, and suddenly, wow, there were lines and indications that there was a structure underneath. So at some points, we had over 200 workers and archaeologists excavating at this site. It's 13 football fields in size. It's from the earliest dynasties. The pyramids you're looking at there are the Great Pyramid of Khufu and the Pyramid of Khafre. The Sphinx is in there, but just sort of below the Great Pyramid. And it's a marker in time. It was built approximately 3000 BC, so it's about 5,000 years old. And now we're going to take a look at a marker in the future. This is the clock of the long now. Has anybody here heard about this project? If you have, raise your hand, and then I'll have some idea. So, okay. So the clock of the long now is designed and is being built. It's intended to run for 10,000 years. And it's entirely mechanical. Its inventor claims it's the slowest computer in the world. And he in fact, was the inventor of massively parallel processing, but fascinated with mechanical processes as well. It's being housed in a mountain. It's a massive project. This is the inventor, Danny Hillis, a wonderful product of MIT. One of his early collaborators was Richard Feynman, the physicist. And there's the man who's funding this project, Jeff Bezos. So hats off to them both, because it's a remarkable piece of engineering being built from incredible materials to endure and operate for 10,000 years into the future. So quite significant. So human time, that's what it says in the upper right corner. We've just looked potentially across a 15,000 year span. So 5,000 years ago, and the clock that's being built now that will last 10,000 years into the future. So we have a 15,000 year time of human monuments to consider, marking past and future. And this is where we are, 2018. I'm marking this point particularly because I want to put a marker right next to it, which is this marker. For artificial general intelligence. And as I'm distinguishing that from artificial intelligence, which is, I think many people are familiar with, which is where machines are, often through evolutionary processes, able to compute in ways that humans cannot think and to achieve really remarkable results. Artificial general intelligence is the term that is to describe when it's human-like, when it's not just a specialized task looking at mammograms or doing other very specific jobs, but is actually like a human. And the word singularity sits in the middle there. And we'll take a look at it in just a moment. But the notion that AI surpasses human intelligence is a daunting one. And the estimates used to be, oh, it'll be 100 years out, and then 80 years out, and now people are saying maybe it's only 30 years out, and I've heard as low as 10. It's still speculative, but I guess people are seeing the rate of change is greater than they may have expected. So in any case, the word in the center, singularity, we're going to focus on that now. And here's a definition. So we've said this already. The point at which AI surpasses human intelligence. And here's another definition. This is in mathematics. A point at which a function takes an infinite value. So I'm going to use a little diagram here just to show a new concept now. So we're starting with singularity. We've got a mathematical, sort of a precise definition of it. But in the lower right, there's an exponential graph, the yellow graph. Right above it is a super exponential graph, and that's when the exponents have exponents themselves. So things get faster, faster, is one way we might say that. So super exponential is a really interesting word. And the reason we're now going to shift from singularity over to super exponential is because one of the places I came across it that kept drawing my attention to it was in some work done at the Santa Fe Institute in New Mexico by Jeffrey West, who's a physicist. He was originally at Los Alamos and then is now at the Santa Fe Institute. And he and his partner or collaborator, Luis Betancourt, have been working on understanding cities from a mathematical standpoint. So what's going on? So they analyzed thousands and thousands of cases and parameters and discovered that there are in fact power laws, which is where you have multiple exponentials describing the growth of cities. It's a very, and here's another fellow who has a TED Talk, and a really interesting one to look at because you get a sense of how deep the studies were. So here are a couple of the takeaways. Every doubling in size increases city efficiency by 15%. So you double it, you get a 15% gain. You double it again, you get another 15% gain. So this is very attractive from a financial standpoint and from a consumer standpoint. If you're getting efficiencies, people want to come and people want to put money in, and that causes a reinforced process for the city to increase. So the observation that he made is this super exponential growth of cities results in singularities, and we're back to singularities again. So this is a worrisome thing because the bad and the ugly, and this is Jeffrey West's wording, I think, also scale to the same 15%. So as things are getting more efficient and faster and better, they're also getting worse. So he says there's a solution to this. Unbounded city growth requires accelerating cycles of innovation to avoid collapse. Now, collapse, when we talk about cities, first people imagine buildings, but it's simply a socioeconomic collapse, that the city will not function for humans properly. It's going to be run out of control. So here's a little graph that Geoffrey West made that shows the accelerating cycles of innovation or paradigm shifts. So he's saying, as things get bad, well, we'll innovate a new technology and that will ameliorate that problem. Okay, then on we go, but the intrinsic property is the city still wants to keep growing at this runaway rate. So another innovation is needed. And the sequence is that you need to have a series of innovations to forestall. And he never says cure, he always uses the word forestall to sort of push back the inevitable. But you'll notice that the green circles are getting closer together as they go up the curves here. So what's happening is that the time between these events, between these singularity type events, is getting shorter and shorter. So innovation has to get faster and faster. We don't know where this ends, but these are the observations of a physicist and a mathematician. So what will these innovations look like? So this is a region of the world that understands innovation quite well, but we're going to take a look at something that's not as well known. So here we are again. You can see we end up with a fairly shallow slope, and then it gets pretty severe at the end. I want you to note the timeline is 20 years. And this is called Longnosed Innovation. So the phrase was coined by Bill Buxton, who's a principal scientist at Microsoft Research Labs. He wrote a paper on it. It was published in Business Week because it had all these implications for a certain type of business. And here's what he had to say. Any technology that's going to have a significant impact in the next 5 years is already at least 15 years old and likely still below the radar. So we'll come back to this. The company that I'm involved with as chairman is GeoSim. It's just past the 15-year mark, and most likely you've never heard of it. But we're starting to see the effects of this long-nosed change. So we'll talk a little bit more about that. And here are the segments that he describes: invention, refinement, augmentation, and productization. So you'll see it's in the last 5 years of that 20-year span is when things take off. But we'll talk about real cities because innovating in the physical city is slow and risky. It's expensive. So if you're going to put bike lanes in a city, it might cost you $20 or $30 or $40 million to do that. It may, in fact, be beneficial, but maybe there are going to be complaints and downsides. We don't know. This is one of the problems of the physical city. But if we have a 3D digital representation of a city, then we have an opportunity to actually run precise models of scenarios of the future where we can try things out. Examples might be with autonomous vehicles or agent-based car models. We can actually look at what a future effect will be. So we're going to block this street, and then what happens to all the traffic so we can reroute it. That's a fairly 2D example, but we'll see more as we go here. So precise visualization of infrastructure and data allows for fast innovation in the digital environment. So here, again, we're going to have to innovate in cities. What's the right way to do that innovation in order to forestall these singularities that Geoffrey West is describing? So I'm going to show you an example, and this is the Vancouver example that was mentioned briefly, and I'll show you afterward how we did this, but I think it's worth, and I'll talk over this a little bit as we go. There's a little background music running, but so that's a digital model of a real city. There are no people, no cars. This is done rendered in a way so that we can show lighting and reflections and so on. Most people think we've just flown a helicopter right down into the city, but this is all numbers. It's data captured, data structured, data rendered. We use laser capture, we reconstruct the geometry of the data that we capture, and we can produce outcomes that look photographically real. So as we're going through this, one of the things I want to mention is that it's nice to have a beautiful model of a city, but what are the ways we can use it? So we'll look at some of that, but every object has an identity, or an IoT sensor looking at air quality. These things can be actually alive in the city. We're running through some examples here, looking at underground, looking at indoors. Here we've scanned a very large music store in Hollywood called Guitar Center. We'll see a little bit more of that. So again, this is entirely digital in its construction, because you'll see there are no cars, no people, and yet it looks very lifelike. So there's a list coming up here right after this little title. It's real estate, tourism, augmented reality, autonomous vehicles, city planning, transportation, sustainability, first responder training. It's a long list of things. That's a subset of about 70 things that we have identified as use cases for a digital city model. So I'm going to show you a little bit about how this works. And there's a lot here, so I'm packing big chunks of information into little boxes here. So we start with air data. We fly an aircraft, and this is a fairly common activity. The surveying of, for GIS has been done this way for a long time. We use new types of instrumentation. We used to use lasers and cameras. Before that, we used standard photogrammetric cameras, for those of you who know that. Now we use a new digital photogrammetric process. It's very recent, very high precision. On the ground, we have two ways. We have an outdoor vehicle, you would think of as like the Google car, and an indoor vehicle that uses the same instrumentation but is on a push cart, so you can just move it around the building and it scans the interior. Now, I want to draw a distinction on the outdoor. When you've seen anybody's vehicle driving down your street, capturing pictures and so on, they move in a continuous way. That's called the push broom, where they just keep going and gather data as they fly, and it's helical scanning often. We do not do that. We do what's called a stop and scan, because one of the keys to being able to have a very, very precise high resolution model is that you need your data to be very precise. So we actually stop the vehicle, engage with satellites. We have an inclinometer that measures the orientation of the vehicle. The laser scans 50 million points of measurement of all around it. We have a camera that is gimbaled around its optical center. So it takes a series of pictures, but they have no seam lines because the optical center is consistent through every image. Okay, so that's a quick look at that. We do data pre-processing for air and ground, and we bring in some auxiliary data. We might want to add some other particular photographs or other information. And we do a fusion process. I'll show you a picture of what the fusion looks like. It's quite interesting in just a couple of minutes. From there, it goes to the human 3D modeling phase. So we were talking about that, the long 15-year line of developing a technology like this. So before we had, the kinds of machine learning processes, much of the process had to be worked out by humans, figuring out how are we going to manage and compress the pipeline so that we could do this in a fast way. But it turns out that to produce the 3D city model, we've added machine learning to the process, and it then looks at what all the humans have done and figures out a way to do that, but 10 times faster. So this has been a very substantial change for us in the last couple of years. All of this is represented in about 3 million lines of proprietary code. So that's an end-to-end process from the first bit, from the capturing data on the street, all the way until we show the 3D city model, and we'll talk about that as we go to what are the way it's represented. Pictures from air data. This is recent. This is from Los Angeles. That's what it looks like when it comes in. It looks like kind of a grainy picture, but in fact, every pixel there is actually measuring distance. So it's a very precise, I think from air we have about 3 centimeter resolution on the ground. At street level, and here's our camera again mounted on a truck, the information density is extremely high. So per square meter, at street level, we take about 2,500 measurement points per square meter. So these are extraordinary amounts of data rolling in. Indoor, this is an airport in the Far East, and here's that you'll notice the top part looks the same. It's basically on a pushcart, so we can navigate all over the place and assemble information. Here's that fusion I was talking about. This is what we call a mega point cloud. Without trying to take a detour into describing what point clouds are, when the laser scans, it builds a model of depth measurement that looks kind of ghostly, and they call it a cloud. The point is that a laser will do that at a particular place, and it's got that area captured. And then when you move down the street and move down the street, there are multiple point clouds that are being generated. And the trick here is that we have found and patented a process to co-register all these sets and then fuse them together. So what we end up with is not just a laser scan of a room like this, but a laser composite of an entire city. So we have measurement data for the entire city that's very precise. And at the end, once we built a city model, we have 2 different ways to deploy it. One might be for professional purposes, where we can actually stream the model of the city, the digital model, out to a user. And for a more consumer-based idea, it's by using what they call cloud rendering, where you might be using your iPad, you can move your fingers, it looks like you're moving through the city, but all the hard work is being done in the cloud in a server that's 1,000 miles away. So that's much more in the realm of a consumer device as opposed to a professional device. In any case, these are all envisioned. But you'll notice in the middle here, it says city-related data and applications. So while we're making these models available, information from the city, traffic patterns, traffic lights, data sensors, IoT sensors, can all be informing the model so that it's showing you what's going on. You can actually see the traffic signals. This is an example. If the signals in the actual city are changing based on software instructions, the digital model of the city can be reflecting the same kind of states. It can know and show the same information. So I talked a little bit about machine learning. I'm going to quickly go through a sequence here to talk about that. Specifically relating to when we capture data from the air. So here I'm showing you, this is work from what is really sort of the industry standard. This is another company's software. And this is a best effort to take air images and construct them so they look like the real thing. But if we look closely at it, you'll see there are lots of errors, lots of missing columns and portals. What we have been able to do is to teach a neural network how to do this. So here's a messy point cloud on the left, but on the right, you'll see the white lines have extracted the information about the geometry of the building. Now that isn't done by a human. The neural network has learned to see what buildings look like and what a roof line is and what a window is and what a door is, and to actually construct on its own that. And this is important because these kinds of geometries are essential to the kind of work that we do. Here I'm going to show you a quick comparison. So everybody knows Google Earth and Street View. And Google Earth looks beautiful because it was shot from an airplane. But when we go down to the street, if we turn off the Street View photographs, this is actually what Google Earth looks like. And you can do this on your computer, but they generally force you to look at the photos. But this is the output of our system. So we have captured it with orders of magnitude more detail and precision. So it creates a very different aesthetic experience. Here's a nice quote. So our company is GeoSim. GeoSim makes the 2 orders of magnitude leap that makes a meaningful difference to the human nervous system. This is a quote from Alan Kay. And Some of you here may know who Alan Kay is. Alan had a team at Xerox, a team of 25 people. On the left is a list of things that they developed, most of which, or many of which, Steve Jobs came in and picked off as the basis for Macintosh. But Alan's team was 25 people. They had 5 years. Xerox spent about 10 to 12 million a year on their team, and the return was $40 trillion. They've been tracking this. So so when Alan rendered this opinion on our work, it was an interesting one, and I'm going to show you why. So here it is again. GeoSim makes the 2 orders of magnitude leap that makes a meaningful difference to the human nervous system. Well, that's the perceptual part of, am I really in a world, or is this kind of a fake thing? When you get to the level of realism that we've accomplished, the implications for this other quote are green box, freeing cognitive processing capacity for application tasks. That's very meaningful. So now, instead of looking at dashboards and symbols and icons and trying to interpret things, I'm actually able to experience a world in a perceptual way. And if what they're saying is correct, then I've just taken a load off my mind. I don't have to be interpreting everything. I now have cognitive bandwidth left to consider problems that I want to solve, innovations that I might want to make. 2 stories of the flood. This is a modern flood, obviously. So flood story 1, and this is Vancouver again, we're referencing. They produced a 143-page report about flood activity, because Vancouver is very at risk in that sense. A lot of areas will be exposed to flooding for multiple reasons having to do with tides and sea level rise, and they're in a very high earthquake probability zone. But this report is static. It's very cognitive. You have to really look at it and drill down. It's 100 pages or more, and it's really written for experts. So flood story 2 is the following. We're now going to go into the world of interactive, perceptual, and where City Council and everyone really can understand what's going on. So here's flood story 2. This is a real-time screen capture off a computer. This is where we're raising the water level in the city. So I can report to you firsthand that when I sat in the city manager's office and ran this little sequence right here, he said, we need to get you over to sustainability right now. And then all of these shots that you're seeing were the result of further conversations with sustainability in the city to put the 143-page report information into a visceral form where people could look at it and have an emotion about what was going to happen. Scenes like this are probable, and this one, the train station, is dire. Other things, applications, so construction, we can visualize new buildings. We're already doing this. I'll show you an example. Traffic simulation. We are already working on autonomous vehicles, because when you have a precise model, you can train vehicles in them. Underground infrastructure, we take city data and visualize it for them so they can see it in a way they haven't seen it before. For city planning, we are in a dialogue with the city of Vancouver where we're actually developers be able to visualize the model and put it in place ahead of time so that the city can look at it. And real estate, here we're showing the value of being able to go into the interior of a building. I mentioned earlier Guitar Center, and here we're looking at a retail application. The notion with retail, here's the Guitar Center store in Hollywood, is to connect up the 3D model of the store with the actual objects that are hanging on the wall and be able to visualize individual guitars, sub-millimeter detail, so you can see the grain and the wood and the strings and the faceplate screws and so on, and then connect it by SKUs to the back office so it becomes part of the database of selling. This is one of the big continuities that we'll have, is going from the large scale to the small scale. Here's another example on the side of retail. So here are some alternative ways of seeing. Once we've got the data, we could do an artist's sketch. Of course, this isn't an artist's work. This is just derived from the data we've collected. But we can do renderings that have nice qualities to it. Here we've changed the focal depth, a depth of field. And maybe we want to look at a monochrome version of that. Maybe we want to take some of the data we've scanned and make it look like an architectural rendering, so we can do that. And here, this was actually a commissioned study wanting to look at where shadows go and how they're going to affect the experience of people in the park. The proposed building casts a different color shadow, and there it comes, it's purple. So now the city can evaluate where all other shadows are versus this new proposed building, so they can see what the impact will be at any given time of day. And you saw the clock running up in the right-hand corner there. We're going quite quickly through the hours. Here, this was a building. They wanted to do some overlay where they take the new building, this is in orange here, and just slide it into where the old building is and put it into place, and then be able to zoom back and look at it from the air and look at it from all different angles around the city. So this is part of what we're doing with the city of Vancouver now. Here's a simple example of when you go from information in 2D to 3D, that all of a sudden you're seeing an entirely different set of offenders in the area of energy consumption. The left side was done in New York, as I think it was part of a Bloomberg study. The right side is our representation of what that looks like when you have detailed information, so you can actually see the energy consumption floor by floor. So just reviewing the details here. At street level, 1 centimeter per pixel visual resolution. 5 to 10 centimeter absolute spatial precision. Real-time navigation and visualization, which means it's like a video game. You can actually just fly through the city or drive through it or walk through it in real time. It's a completely fluid environment. And full immersion in VR. And for this one, I'm going to stand up just for a second, because what we've done in first responder training is we actually put people in their VR headsets in a big space, untethered. So it's all using wireless. And we make the buildings about this high so that you're like Godzilla and you're able to walk through the buildings. Now this is all stereoscopic, you're seeing it as though you're there. You can look at an event that might be transpiring, shrink yourself down, and so you're now looking up at the buildings. The scalability is really remarkable, but it changes the way you understand the situation when you can represent it in a different way. So semantic capabilities. Objects have identities. This is the part I was saying where it's nice to have a pretty model, but when you can count the number of windows on a building or the number of parking meters that are operational at any given moment on a street from end to end, you have a powerful model of it echoes the reality. So I'm going to look at past, present, and future. So cities have databases they've collected, and one would be that, for instance, in Vancouver, they've collected all the trees. So we just import that whole flat database, which tells locations and so on. And now every tree that you look at in the Vancouver, you can touch it, and it'll reveal information about when it was planted, what its diameter is, what type of tree it is, and so on. In the present, real-time data is the goal. So with the world of Internet of Things, IoT sensors, we want to be able to bring that data immediately into the model so you can be looking at it in the context of the city itself. So now, if you have cameras, if you have infrared sensors or temperature sensors, all that information is flowing simultaneously inside the city model. And then, for the future, we talked about this briefly, simulations of future events. Because of the precision of this model, and the ability to understand, perceptually what the implications will be, we can run scenarios that look at what ifs. What if this happened? What if the water rise goes into a transformer and shuts down this part of the city, and you have these sort of first, second, and third order effects. So I want to talk about second order effects. I found this really simple one that James Stuber had put online. The first order is, from using Google Maps, is you never get lost. But the second order effect is you lose an understanding of the area and have no idea how to get around if your phone dies. So it's really nice and simple, but it goes on like that, where effects have other effects, actions have effects that have other effects. And so humans are notoriously bad at that. It's one of those places where we're just cognitively challenged. We're not good at anticipating second and third order effects. So the solution is to run simulations in the city model to discover these second and third order effects ahead of time. So I want to talk about analog and digital again briefly. This picture on the left is meant to represent a photograph of the city of Vancouver, which is the way we experience the world, right? So we're here, we can knock on the table, we have a sense of being there. These are analog experiences, meaning it's not been sliced into bits and analyzed. Our organism is an analog being. But in the opportunity of scanning the whole city to produce a copy of it, we have this incredible moment for introducing new information, semantics, data, navigation, interaction. We can apply artificial intelligence to aspects of the city process. And then output back in analog again. If I put those headsets on, I feel as though I'm in the world again and I'm moving around, but now it's imbued with all of this beautiful data and opportunity to understand the world in different ways. So I want to show you one more city-like environment. This is Quest University in Canada. And this was, again, just done by the same process. Aircraft, a vehicle driving around, a vehicle driving inside. And here it's unusual because you can see right through the building in some cases. It's in a beautiful place north of Vancouver. But we've allowed this integration of interior and exterior so you can flow seamlessly through all the rooms in the university. They were interested particularly because more than 50% of the students come from outside of Canada. And what they would like to have is an experience ahead of time. What's my dorm room going to look like? Where's my professor's office? What's the cafeteria like? So by scanning and representing it this way and allowing them to navigate freely through it, it gives them an advanced look, really a feel for that perceptual sense of the university that's very different than looking at a brochure or looking at photographs. So this will run for perhaps another minute where it shows details of the inner workings. So that's a university campus. So what are the implications at a global scale? So here's the way we're seeing it. As soon as you've digitized a city and made a model of it that's interactive, that can communicate, you must think about the global network of cities. And interestingly, I had a conversation with a physicist at SAP who said, you need to think about 26,000 cities. That's roughly the scale. I had never heard that number before. It was amazing to me. But the notion is that when you build a network of cities, you now have an opportunity for each of these cities to communicate with each other. Best practices developed in one can be shared across the whole network. It's a game-changing proposition to think about it on a global scale. We're looking at one node here. We've examined Vancouver, which is the first of its kind. The network will be a tens of trillions of dollars again proposition. So that's a little bit of a look ahead. That's me speculating, but that's what I think may come. So back to the beginning. We talked about a valid but unexpected alternate path. So I was at a conference here a couple of years ago in the Presidio, and was going through this beautiful building, and I made a left turn and looked into the hallway, and I took a photograph of what I saw because I didn't expect what I was seeing. And we were talking about illusions today and how things can be striking and kind of unexpected. And that's what I saw. So I actually took out a ruler last night because I knew this thing was meant to look like all the lines are wavy, and that whoever designed this bathroom understood exactly what they were doing. You can take a ruler from the bottom of this photo and go up by level, by level, by level, and these lines are perfectly straight. And yet, they look like they're converging and diverging, and it's a wonderful illusion. In any case, that's the note on which I'd like to close, is that I think it's a good one. So thank you.
Thank you so much, Matthew.